Welcome everyone to the Introduction to Multibody Dynamics. So this will be a webinar. I'll be just focusing on the basics today of what all will be covered in the course. So let's get started. Basically these days, CAE is gaining tremendous importance in over the physical testing. So if you are involved in physical testing when compared to CAE, CAE is trying to gain more importance because it helps in saving time and also the huge investments that the companies will be involved in setting up the test. So it's very important for the OEMs. So by OEMs, I mean by original equipment manufacturers like Ford, GM, Chrysler. So they are showing this inclination towards CAE compared to testing. And CAE is a very vast domain. It includes the domains like the subdomains like finite element analysis, computational fluid dynamics, optimization, and our today's topic of discussion, which is multibody dynamics. So both multibody dynamics and FEA are very closely related to each other, but they are totally two different worlds. The current market trend, it has shown tremendous opportunities for us, for those who are well versed in both FEA and MBD. So if you go to the job market now, people who are just preferring FEA experts, they are the people, but people having both MBD as well as FEA exposure, they are being preferred compared to the person with just FEA background. So such applicants will basically have more edge over the others with just the FEA knowledge. So on the high level, MBD is more abstract in nature, while FEA is more complex and computationally very heavy. So this is like the basic introduction. So now let's understand what MBD is. So multibody dynamics or multibody simulation is basically the study of mechanical systems caused by the external forces and motion that are acting on the system. So when the force excitations or the motion excitations, they are acting on the system. So the study of this entire process, it's called multibody dynamics or multibody dynamic simulation. So the most important characteristic of all these systems is that they undergo large overall motion that is comparable to their dimensions. So the MBD systems, they consist of bodies or links that are connected to each other by constraints. So they can be either joints or motions. And these constraints basically restrict the relative motion between the two entities. So the analysis of the working of these systems is the study of multibody dynamics. And one of the major advantages, or I can say applications of MBD, is that we can generate the loads in MBD analysis, which can be captured through the simulation, and they can be in turn used as an input for the FE models, though I mean the finite element models. So let's now take a deep dive into the differences between multibody dynamics and finite element analysis. So I hope most of you over here are familiar with finite element analysis because it's usually incorporated in your work course or your degree, but MBD is usually not included in most of the courses, and people have now realized the importance of MBD and they're trying to include it in their syllabus. So let's just go over the differences between these two. So in MBD simulations, we concentrate on the performance of the entire system. The system performance will be taken into consideration. For example, if you consider the simulation of a robotic arm, we obtain outputs such as forces, acceleration, velocities, torques in the joints, etc. Whereas in FEA, we are more focused on the structural performance of the entire system. So, and moving on to the second point, it usually takes some time for those people who are deeply involved in FEA. So say you're an FEA engineer in a particular company, then it takes some time for those people to enter into the MBD world, because even though they are so totally closely related, but they're two different worlds. For instances, we have an example here. The word system, it means different for an MBD engineer, and it gives a totally different meaning for a FEA engineer. So for a FEA engineer, system means a coordinate system, right? But for an MBD engineer, so system refers to reusable collection of modeling entities. So all the modeling entities put together, it basically forms a system. And in MBD, it is basically used for abstract visualization, wherein there's no requirement for you to mesh. So a person who's not well versed with meshing, you don't have to, basically learn meshing and stuff to learn MBD here. So it's just as.
Hey, Sushant. I
Yep.
apologize for interrupting you. So there should be an option called as more, and there will be an option called disable participant annotation.
Yeah, sure.
Can you just, the other thing you can do is you can just stop sharing your screen for a second and then restart the sharing process so that you can get rid of these lines.
Okay.
Guys, again, it would be great if you don't play with the annotation tool while, the presenter is presenting. Please be courteous. If you have any questions, please make use of the chat window. That is where I want all of you to type in your questions. We will be stopping after Sushant covers maybe 2 to 3 more slides, and we'll be answering all those questions. Sushant, did you disable participant annotation?
Yes, I did.
Okay, perfect, Sushant. Please carry on.
Okay. So yes, let's get back to the slide. So I was explaining about the third point. So, and I was talking about the point wherein you don't need to learn meshing to do MBD, whereas in FEA you need to have a basics of even meshing. You need to learn meshing to become an FEA engineer. So in MBD, there's no need of meshing. It's just abstract visualization of the entire model. But in FEA, we mesh the model and go to the precise visualization. And the MBD simulations are faster when compared to the FEA results, because in my company now I'm running an optimization which has been running for like 200 hours and still it is not converged. So they can be really slow because of the extent of precision. So FEA results will be slower when compared to the MBD results. And next, coming to the last point. So in MBD, there are some instances. For example, when you come to topics on the complex topics on contacts and flex bodies, where we need models to be meshed. So here, the result accuracy is independent of the mesh size, and the course I'll be teaching here, it'll be taught using Altair's Multibody Dynamics software, which is Motion View, Motion Solve. So which automatically meshes the model once you bring in your CAD import from any of the files. So you don't have to worry about the meshing here. And here, the last point what I was talking about is the result accuracy is independent of the mesh size in MBD, whereas in FEA, it is proportional to the mesh size. So these are the basic differences between the MBD and FEA. So the current slide just shows the pictorial representation of MBD when compared to FEA. So MBD is faster and simple compared to FEA, which is more time consuming, and it's difficult due to the complexities in the meshing. And just to make things clear, I'm not trying to downsize FEA in these slides. I'm just trying to show that show the differences between those two, like both the pros and cons involved in MBD and FEA. So now I'll be moving on to the applications. So before I start with applications, I can take any questions from your end.
Sure, Sushant. So we have a question from Nitin Balaji. The question is, what is the best multi-body dynamics tool or solver in market at present?
Nitin, the answer to that, I mean, it's a very difficult question. Like no one software is like the best solver or the preprocessor for MBD. We have one of the most popular ones is Adams. We have different types of Adams there, like in a sense, Adams car, Adams chassis, etc. And from Altair, we have the competitor software, which is Motion View, Motion Solve, which is equally good when compared to Adams. So yeah, there's no really the best tool as such, because in CAE world, new tools keep coming up, and one tool is always better when compared to the other. Like there are both pros and cons. Yeah.
Okay. All right. So there is another question from Varun Sai, and I think his question, he hasn't asked it correctly, so I'll try to ask it for him.
Yeah.
With multi-body dynamics and finite element analysis or structural analysis, can we expect the same results?
Yes. So when you try to solve a problem using MBD and FEM, you can expect the same results, but it will be at a loss of an accuracy, because you can model accurate models even in FEA, I mean, even in MBD using flexible bodies. I'll come to that in the later part of this presentation. So you can do that, but it is a little more complex when compared to using rigid bodies. So it's like when you're trying to basically run a simulation and get to know the first-hand results of it. So then it's always better to go with MBD, and then you can deep dive by using your FEA.
Okay, perfect. We'll take one more question for this particular round. Again,
Right.
from Nitin. Is there any open source code for multibody dynamics?
Nitin, I am actually not aware of any open source code for MBD. The ones which I know are all licensed. Like we need to buy the license from the companies. So Adams is from MSC, and Motion Solve is from Altair. So we need to buy these licenses from them.
Okay, all right, Sushant. So there are a couple more minor questions, which I think I would be able to handle it just by typing it in the comment section. So you can please carry on.
Sure. Thanks, Adam.
Yeah.
Okay. So let's continue. So now I'll be describing about, or I'll be explaining about the industrial applications of MBD. So one of the major uses of MBD simulation is the automotive world. Okay, so before I start talking about this, I want some inputs from your end so that I want to know that you guys are also involved in this webinar, because I always like my webinars to be interactive. So can anybody tell me some of the names of popular suspension systems here? Anyone from the audience? You can just give me some names that you're familiar with.
So we have double. Okay, you're seeing the comments.
Yeah, I'm seeing the comments. Yeah, sure. So double wishbone, yes, okay. That's one of them. MacPherson, yes, great. Okay, so it seems like you guys are aware of the different suspension systems, the popular ones, yes. Okay, thank you guys. So most of these are already available. So the advantage of using Altair's Motion View and Motion Solve is because some of these popular suspension, for example, the double wishbone suspension, the MacPherson suspension, these are already available in the MBD software library in Motion View, and you can directly use them for analysis. So there's no need to waste time for building the model and then trying to analyze it. So you have already the built-in models in the MBD software library. You can just import that and start doing your analysis on that. So that's the advantage of Motion View here. And so MBD simulation is basically also widely used in the vehicle dynamics analysis. So I hope you're all familiar with, or somewhat you have a fair idea of what vehicle dynamics is. So either it can be the component level, such as suspension system or the steering system analysis. So wherein you'll have to determine the stress and strain in the control arm. And it can also be for a full vehicle MBD, like the handling analysis, wherein you'll have to calculate the body roll, pitch, etc. So I think here, if I just click on the side, you can see some of the examples. So on the first example, which you see on the left-hand corner is the suspension analysis. So the steering is also included here. So it's a suspension and the steering system analysis. So, and this analysis in particular is the static ride analysis, which is one of the most popular analysis in suspension analysis. And the second one, what you see here is dealing with engine dynamics, wherein you can get the stresses that are created when the simulation happens, and also the forces that are exerted on the mounts. So this is under the engine dynamics. And full vehicle MBD, as I mentioned, you can calculate the body roll, pitch, etc. So moving on to the next application, that's aviation. So basically MBD is also widely used in the aerospace as well as in the aviation industry. So in the aviation industry, it's mainly used to design and analyze the mechanisms of landing gears, seat ejection mechanism, flight simulators, and also the helicopter fuselage. So all these can be simulated in MBD, and you can get the forces that will be generated at the tires when when an aeroplane lands on the ground. So all these can be obtained by doing the MBD analysis. So moving on to our next application, defense. So MBD again plays a major role in the defense sector as well. And most of our defense industries use this technique. So for instance, say we want to build a system using MBD that is used to track the target and hit the target after the missile is launched. So we can predict the parameters such as angle, velocity with which the missile has to be launched in order to hit the target. And all these parameters can be calculated, but of course with some assumptions. And you can also model and also simulate the complicated battlefield vehicles using MBD. Next, moving on to our next application, which is manufacturing. So in manufacturing, MBD is used for designing chain and the belt drive systems, the conveyor belts, and also other machinery equipments. So in MSc Adams, there are also built-in macros. So that's one more advantage of using Adams over Motion View, wherein we can build macro. There are already built-in macros there for the chain and the belt drive systems, and you can also build your own macro to create new systems once you become go to that advanced user level. So these macros can also be built in Motion View as well, but some of these are readily available in Adams. Okay, now for the guys who are interested in the robotics industry and the heavy equipment industry, so MBD is also used over here, wherein you can see these animations. So the CAD geometry of this robotic arm, it can be directly imported from any of the CAD softwares into the MBD, and then the joints and motions need to be created here. And once that is done, you can simulate the robotic arm so that it can pick up this box. So this trajectory can be defined in Motion View, basically using a curve. And once this is defined, we can get to the simulation of it, wherein we can analyze the forces that is required to pick up this box by this robotic arm. And we can also analyze with what velocity this has to travel and how much time it can pick up this box. All these analysis can be done easily in MBD. And also in the second animation over here, you can see that there is a crane mechanism, and you can calculate the stresses that are induced in this arm. But this arm here, it should be modeled using flexible bodies. So I'll come to that in a while, wherein what the difference between the rigid bodies and the flexible bodies and why we need to use flexible bodies and stuff. So yeah, you can get the stresses that are generated in this arm. So that's one of the examples I'm giving here. And we can also set up some DOE, that's the design of experiments in MBD tools. So to perform the sensitivity analysis, such as the length, the proper length, and the width of this arm that has to be created. Like if you want to change the design to make it more optimized, then you can do some DOE analysis in MBD itself to finalize the most optimum design for this particular model. So all these things can be done using MBD. And now coming to the last applications. So those who are in the medical industry. So it's also, MBD is also advancing into the medical industries in the field of orthopedics, human locomotion, and injury biomechanics. So for instance, in injury biomechanics, MBD is used to create a dummy of a human sitting in a car. And then we can do a crash analysis to analyze the damage that is caused due to this crash on the various parts of human body. So this analysis will be basically using a combination of FEA and MBD. So this is like the wide range of domains where MBD is used in. So I can maybe stop here, and moving on, before I move on to the next phase of this presentation, I can take in some questions.
All right. Thank you, Sushant. So I think we have a few good questions. So one of the questions is from Mivin. So he basically looked at the slide where, for multibody dynamics, you had a picture of a hare, and for finite element analysis, a turtle. So I think he wants, he wants your comment on the differences in computational time.
Yes. So if you want to talk about computational time, so it depends on the complexity of the structure and how finely. For example, here I've just taken an example of the piston, connecting rod, and the crankshaft. So, and the cylinder bore here. So if you basically mesh this model very finely, and if you want very accurate results, then in FEA it is going to take like 10 times more time when compared to what it takes in MBD, because MBD will be just using abstract visualization and then will be performing the analysis. So you can get 80% accuracy of the results in, but you will have the advantage of the time. Like you can do it in a very fast rate. So this will be like 10 times slower when compared to MBD. So that's why if put a turtle here, saying that it's slower when compared to the hare.
Yeah. Okay. All right. So I think we have Akshay and Ankit kind of asking the same questions. So correct me if I'm wrong, but I think there's some kind of a library in motion view, right, where geometries already exist.
Right.
So I think Akshay and Ankit want to know that, is it possible to modify these suspension system geometries that are available in the library?
Yes, absolutely. That's totally possible. So you can get like the working model, which is already built in, and you can change it accordingly, like according to whatever values you want to give. If you want to change the hard points and give different, sizes for that, you can all do that in now. It's all available in Motion View. You can do that.
Okay. All right. Perfect. So I think we'll take two more questions. I think these two are both interesting. So first is from Apurva. In flexible body analysis, how do we decide which part should be treated as rigid and which part is treated as flexible?
Okay, that's actually a very great question. So we need to use our engineering judgment. For example, if I go back to this slide, so here the major thing that we want to see, like if you use our engineering judgment, we can get to know the major stresses that happen in this area. So instead of making the entire model as flexible, which is going to be really complex and it might take the same time when compared to the FEA analysis. So to make use of MBD, we need to use our engineering judgment and need to know what part of the body needs to be converted to a flexible component, and then we can analyze. So if you want the stresses in this component, we can change, we can just consider the arm to be flexible and we can analyze the results. So basically we have to do a sensitivity study there. So I hope this answers your question, but I need actually more time to answer that. I mean, it will take like at least 15 minutes time. So if you can register for a course, then you'll get an answer to that in detail. Yeah.
Right. Exactly. So yeah, we will be talking about the course that we offer on multibody dynamics, and definitely consider that.
Yeah, because that question, it really takes a long time to ask, and that is a really good question from her end. Yeah.
Okay, great. So we will take one last question in this particular point of the presentation. This is from Raj Mehta. In order to obtain dynamic stresses, won't I need to mesh the components in multibody dynamics as well? If so, how are MBD results mesh size independent?
Okay, again, another very good question. So yes, the answer to that is yes, you need to mesh that in MBD as well. But as I mentioned earlier, in motion view will take care of it. Like when you create a flexible, because the first thing is, if you want stresses induced in a particular component, then we need to use flexible bodies. So when you generate flexible bodies, the mesh size, or what do you say, the condensation of the whole part happens, and we can get the actual stresses and the strains induced in the particular component. We can recover that. So all this will be taken care in the software itself. So there's no need to mesh it separately and stuff. So all this will be taken care.
Okay, perfect. Sushant, you can carry on.
Yeah, okay. So let's move on to the evolution of multibody dynamics. So how it's evolved through the years. So traditionally, multibody dynamics used to only deal with the rigid body dynamics. Hence, it was not very popular. So here, the results were kind of not very accurate. And also in the cases of simulations involving large deformations and displacements, the rigid body dynamics couldn't handle that. So, and the main thing is rigid body dynamics also couldn't capture the stress and strain effects, like what I was just trying to explain earlier. They couldn't accommodate the stress and strain effects on the parts. So thus the usage of MBD was limited a few years ago because of this technical barrier. But however, with the discovery of flexible bodies, MBD simulation has gained new importance and it's began to expand its scope. So more and more industries and engineers have become increasingly interested in MBD and also the flexible bodies. So because the flexible bodies can capture both large deformation as well as the stress and strain effects, and also produce accurate and more robust results when compared to the rigid body dynamics. And the core simulation, this is right now, it's in an era of core simulation, wherein the engineers are trying to merge the 3D world and the MBD world. So, and the 1D world. So what I mean by that, I'll be coming to that in a few slides later about the core simulation. So I will give you more details on that in the upcoming slides. And lastly, coming to the user subroutines, this is mostly done by the advanced users. So this is basically defining functions which will help in automating a process. And it is increasing in number in these days because people are moving towards automation. So this is how MBD has evolved over years, from rigid body dynamics to the use of subroutines. So let's now take each of these in detail. So if I want to introduce you to the rigid body dynamics, it's basically, it was used traditionally as in MBD analysis. Rigid body is a 6 degree of freedom element when both the masses as well as the inertias are significant. But here the deformation is negligible. Hence, it cannot capture large deformations and also the stress and strain effects. And rigid bodies, they have both a position and orientation, and it's basically represented by two parameters, that is the center of mass and the orientation. Now coming to the flexible bodies. So first, I want to give a definition of flexible bodies, and I hope you'll be able to understand what it is. So it is basically a model representation of an FE model. So what happens is the finite element model will be condensed by using some component mode synthesis methods. They are called as the CMS methods. So we'll be using that, and we'll be condensing the large degree of freedom FE model into the MBD model or a flexible body, and we'll be using that for our analysis in MBD. So it is used with various CAE solvers like Adams, MotionSolve, OptiStruct, etc., to capture these large deformations and the stress and strain effects on the body. And the concept behind flexible body is modal superposition. Okay, and now coming to the uses of flexible bodies. So the first and the foremost use of flexible body is it can capture large deformations, and it increases the accuracy of the load predictions. It helps in determining the stress and strain distribution in the body, and it also helps in removing the redundant constraints. So, okay, so I mentioned the word redundant constraints. So I want someone from the audience to tell me if you have any idea what redundant constraints are. So
all
you
right,
can just...
let's all use the chat box and try to answer this question, please.
So I'll just repeat my question. What are redundant constraints?
No answer is bad answer. If you have an idea, just type it out and we'll let you know if it's correct or not.
Okay, that's the literal meaning of it, but in technically, what do you mean by that? I think, yeah, Jassim answered that, but the constraints that are not important, exactly right. That's the literal meaning. So I want to know technically what it means. No, that's not the answer. Not exactly. Okay, Varun also is telling the constraints that can be omitted. Yes, very close. Okay, I'm getting some close answers, but let me now just give you in an example, explain an example, and then you will be able to understand what redundant constraints are. So for example, in the physical world, if you take the simulation of a door with 3 hinges, so if you try to model that in MBD, then you can, if you put 3 revolute joints there, right? Because a revolute joint will basically allow the rotation along 1 degree of freedom. So the door with the hinge can be modeled in MBD by using a revolute joint, right? So instead of using 1 revolute joint, if you try to actually match the physical world and put 3 revolute joints, then 2 of those 3 revolute joints are redundant because they're all trying to do the same thing, right? Because it's just allowing the motion in 1 particular degree of freedom, and 2 of those are redundant constraints. So if you introduce redundant constraints in MBD, then the solver faces a lot of problem and you might not get accurate results. So by using these flexible bodies, you can help to remove those redundant constraints and make your predictions more accurate. So I hope you got an idea of what redundant constraints are and how flexible bodies will be useful. And finally, the last application is that it produces very accurate, very good results, like in a sense, highly accurate results. So these are some of the main pros of using flexible bodies while over the rigid bodies. Okay. Let's move on to the next slide. Okay. Now I'll be talking about the contact simulation. So, which is also another another important topic in multibody dynamics. So, in contact simulation, we have the 2D contacts as well as the 3D contacts. So, when two bodies are in a contact at a point or along a path, then the relative motion of these coincident points are not the same. So then we call it as 2D contact. So we can model this cam follower mechanism using the 2D contact, and the curve profile of this cam interacts with the curve profile of this roller. So this is the cam and this is the roller. So the curve profile that we generate for this cam will interact with the curve profile that we generate for this roller. So this is an example of a 2D contact. And another example is the robotic arm, which will follow the point to curve mechanism to pick up an object at different locations. Okay. And moving on to the 3D contacts, which are more complex and computationally heavy when compared to the 3D contacts, compared to the 2D contacts. So there is an algorithm here called the contact collision algorithm, which will search for the proximity. Okay, it will search for the proximity between the interacting parts, and then when there is a penetration, a force based on that penetration will be generated. And also it will depend upon the contact properties that you define in the software. So depending on that, a force will be generated, and you can get the forces that will be generated because of these contacts. A typical example here is of a ball bearing. And so here, I think the image is not very clear. So it is this ball bearing, it has 6 balls here. And once you try to build this model and simulate it, you can get the forces on these balls, the 6 balls which are inside. You can get the forces on each of these balls. And it will help you to drive the design in the right direction. So moving on to our next slide. So core simulation. This is again an evolving domain in MBD. It's not still completely evolved. It is right now the era of core simulation. So before I try to explain what this is and try to show you the animation here, so I think this should give you an idea, right? And if anyone has any experience working on core simulation, can you tell me what core simulation is? Anyone from the audience?
Sushant, as you're waiting
right.
for the answer, I think there is a couple of comments from Apurva.
Okay.
Like I think when you are showing the ball bearing, I think under the heading of 3D contacts, right. I think the question was, but a ball bearing has a point contact? Question mark. I think they're asking like, why is a ball bearing a 3D contact?
That's because the ball bearing, even if it has a single point of contact, in the sense, it cannot have a single point of contact, because if you consider the ball as a 3D sphere, then if you consider the outer rim, the middle rim and the inner race, okay, it's called the outer race here, the blue part, the green part is the middle race, and the red part is the inner race. So the ball is having contacts at all these 3 locations. So it cannot be just point contact. So it's like a sphere, and it's interacting all these 3 regions. So then we have to define a 3D contact there and not just a point contact. That's what I'm trying to say. I am basically talking about the ball bearing for this particular simulation. Maybe there can be an example where it can have a single point of contact, but for this example, it will be a 3D contact.
Okay, perfect, guys. I hope that makes sense. And Sushant, you can just go back to your question.
Yes, my question was, anyone has any idea about core simulation? What core simulation is?
Guys, if you don't know the answer, you can just type in no as well. That is also a valid answer. So that way we can get some feedback.
Okay. Okay, no problem. I'll just try to explain. I'll just give you this example so that it will be very clear. So what I'm trying to do here is a robot design. Okay. And I hope everyone here, or some of you guys over here, are familiar with MATLAB and Simulink. Okay. So in Altair, we have the same tools, but they are the competitive softwares. They are called Compose and Activate. So Compose is basically for scripting, and Activate is like for Simulink, for building the logic blocks and connecting it to get the outputs. Okay. So what happens is in core simulation, now the engineers, they're trying to merge the 3D world and the 1D world. So the 3D world is the MBD world or the FEA world, wherein we import these CAD models from different softwares and we try to mesh them and try to get the results. So they are trying to basically merge this compared and with the 1D world. So in 1D, this whole structure will be in the form of this logic block, and we can give various inputs and get the various outputs. So you can just observe here, and let's play the simulation. So this robotic arm, it's trying to pick up the sheet. Okay. So what happens is we can model this entire 3D model in MBD using motion view. And then the inputs and the outputs can be obtained in Simulink, which is similar to Activate and Motion Solve. A combination of this will give you the results. For example, if you want robot suction forces or the robot arm angles. So all these can be obtained in Simulink. So it'll be basically an interaction between the MBD and the 1D tools like Simulink or Activate, Compose. So you can also write in scripts, you can also write in scripts in Compose. You can attach it in MBD and also get the results. So it's basically a combination of using the 3D tools with the 1D tools. So this is what is happening right now. So I think you got a fair knowledge of what I'm trying to refer to as co-simulation. Okay, so this is just one of the examples. There's still more complicated things that are being done now. So even this can be done using motion view, motion solve, or I don't know, I haven't worked on this aspect in Adams. So I don't know how Adams is, how good Adams is at this particular concept, but motion view, motion solve, it really has very good options to do co-simulation. Okay. And lastly, coming to user subroutines. So user subroutines, they can be written in the MBD software, which will allow the program to be customized for various applications. And these can be written in any of the scripting languages like C, C++, Python, MATLAB. So these codes can be used to automate and process. So, and it will be very useful for you in industries when you're trying to do the same stuff every day. And if you write a script for it, and if you have an automation script, you can just run the script and it does the job for you. So these are very helpful, but you need advanced knowledge to create the user subroutines. Okay. So before I move into this, I can take any questions if you guys have any questions.
So we have one question from Nitin. What does automation mean in simulation side? I don't get it.
Yes. So for example, say you're trying to, if you talk about the engine dynamics and you're dealing with NVH, think that you're trying to get the vibration at the various engine mounts. So when you are talking about this, you'll have to run the same code every day, or whenever you want to do the analysis, you need to run the same script to get the answer. So instead of that, you can write one script which will, if you just change the model name, it should be able to do the analysis for even that. Like you don't have to you don't have to write the script again and again, or you don't have to run the same analysis for different models. Just there should be a master script to which different model files can be attached, and you have to just get the results. So that's what I mean by automation. I hope I answered your question. Okay.
Okay, so let us see. I think there are a couple of questions that are not that meaningful, so I'm just going to skip that. Samir Gupta, how is it different from doing a simulation in ANSYS? I guess that question is a bit vague, but
yeah, I mean, it depends on what type of simulation you're doing in ANSYS. Like, is it structural, CFD oriented? Yeah, it totally depends on that. I really don't know how to answer that question. So yeah, here this motion view, motion solve, or whatever I'm talking right now is about multibody dynamics. It's a completely different domain, and you need specific solvers and pre-processing softwares to do these simulations.
Okay, so I'll just make a comment before I let you continue. So
yeah,
guys,
sure.
Sushant's time is really valuable. He has been gracious enough to agree and do this presentation for us. I'm disturbing him during a Sunday, so let's put a little bit more effort while we're asking questions, right? So, okay, so let's just keep that in mind. And Sushant, you can just carry on.
Yeah, sure. So now coming to we'll just deep dive into MBD. So till now I was just explaining about the applications, the users and stuff. So now coming to the actual MBD. So here these are the common components that are required to model any MBD model. Okay, so they require force elements, a reference frame, which is also a coordinate system, the hard points, markers to define the location and orientation of an entity, and the bodies, either a rigid body or a flexible body, and then the constraints, which are nothing but joints and the motions. So all these components are the building blocks in constructing an MBD model. Okay. So now let's talk about what is a multibody dynamics system. Okay. So now we are in a position to answer this question. So a collection of all the entities, which I mentioned in the previous slide, that is the bodies, constraints, markers, points, etc., are connected to each other by either joints or constraints and have relative motion between them. All these can be called multibody dynamic system. So all these can be modeled in your software and you can run the simulation and analyze the results. Okay. So here is an animation of multibody dynamic system. So wherein I'm considering a flexible beam. So this blue part, what you can see here is a flexible beam. So this flexible beam is connected to this sliding mass here, which is sandwiched between these two gray blocks using this prismatic joint. So prismatic joint is this sliding or translation joint. Okay. So the other end of this flexible beam is connected to this particular link through a revolute joint. Okay, so you can see how this simulation works. So you'll have a reciprocating motion here, which is converted into a rotary motion. So something similar to your, the piston moving inside a cylinder, right? The piston has a reciprocating motion, which is converted into the rotary motion here. Okay, so this is one of the simple simulations, and based on after building this model and simulating it, you can get the results like the forces acting on this particular joint or the velocity with which it is traveling. All these outputs can be requested in the software. Okay, now let's go to this this slide wherein I'll be explaining about the equations that govern the MBD simulation. So usually in my classes, I just don't like explaining the software part of it or just those details, because I like to go from the scratch, like what is the theory behind it. So if you want to concentrate on what the theory is behind it, then it's about the Newton's second law of motion. Okay, so the dynamic behavior of any multibody dynamic system is described using equations of motion. And the key formula for it is based on the Newton's second law of motion. And the equations for the general motion of a single body coupled with the constraint equations, they get written out in the solver, okay, which is motion solve. That's a solver. So what you'll be working on as in the graphical user interface is motion view, which is the pre-processing software. And the solver here will be motion solve. So when you create a constraint and a joint or a motion, whatever you create on the graphical user interface, it will be written out in terms of equations in the solver. And those equations, they get solved every time you run the simulation. So the key thing what I wanted to say here is everything is dependent on the Newton's second law of motion. Okay. So now I'll be quickly explaining the different types of simulations that are available in MBD. So they are the kinematic simulation, dynamic simulation, static simulation, quasi-static simulation, linear simulation, or a complex simulation. A complex simulation is basically a combination of two or more simulation types. So I'll be talking about each of these simulations in detail. So let's go to the next slide. So kinematic simulations. So kinematic simulation is one where it has just 1 degree of freedom. It has just 0 degree of freedom. Okay. So the model that you build will have 0 degree of freedom. And it is basically a pure geometric study to analyze the forces such as position, velocity, and acceleration of the entities in the mechanism. So here the forces will be calculated as a consequence of motion, which is basically a function of time. And the non-linear algebraic equations, they are solved by the Newton-Raphson method in the background by the solver, and the resulting solution will be robust in nature. So here applications using this kinematic simulation will be a robot design or a cam profile design, etc. All these fall under the kinematic simulation. So when you build a model and when you say check model before running the simulation, you can get a report of how many DOFs are there in the model, and the ones with 0 degree of freedom, they fall under the kinematic simulation. Okay. Now moving on to the dynamic simulation. So dynamic simulation is basically the study of motion of a system as a consequence of applied forces and inertia forces. Okay, so that's a definition for dynamic simulation. So it is always applicable to models with 1 or more degrees of freedom. So here the degree of freedom should be greater than 0. So it can be 1 or more. And in dynamic simulation, the forces applied, they'll affect the accelerations. And these accelerations will be integrated to get the velocities, and the velocities will be in turn integrated to get displacements. So after running a dynamic simulation, you can request for either velocity, acceleration, or displacements. Okay, and here some of the applications what I can mention is about the piston dynamics or the vehicle dynamics. They need to use the dynamic simulation. Okay, now moving on to the static simulation. So static means rest. So it is basically the study of equilibrium conditions of a system at rest. So in this simulation, the system velocities and the accelerations are considered 0. And a static force balance problem will be solved by the solver. So the applications here, you can consider the simulation of the forces on a system at rest. For example, a model of an apartment or a static stone. So you can, all these examples, they come under static simulation. And now moving on to the quasi-static simulation. So quasi means almost, and static means at rest. So basically, it's a study of equilibrium conditions of slowly moving system. So in this type of simulation, the forces are a function of time and velocity. The forces will be a function of time, and the velocity or the inertia effects will be negligible. Okay, and the governing equations will be algebraic in nature, and some of the applications, popular applications using quasi-static simulation are the suspension design analysis and the stability analysis, and we have some of the steady state simulations. So all these can be done using the quasi-static simulation. And lastly, we have the linear simulation. So if you know something about the NVH domain, then you'll be familiar with linear simulation. So it is basically the study of vibration modes of a system at any operating point. So it involves evaluation of the transfer function of a system at any specified operating point. So this solution, the way how the solution is computed, is divided into two steps. The first step is to linearize the equations of motion at a point. And the second step is the eigenvalue problem will be solved to obtain the mode shapes and the frequencies of the system. So as I mentioned earlier, the applications here is the stability analysis, or it is widely used in NVH analysis.